Dear learners, welcome to our NPTEL course on Science Communication, Research Productivity and Data Analytics using open source software. Now, we have covered science communication, it's important, why do we need different metrics and bibliometrics and its application. Now we are moving to scientometrics. Scientometrics is basically a subset of bibliometrics. Scientometrics is a branch of bibliometrics that focus especially on quantitative analysis of science and scientific research. As Pritchard said in bibliometrics, it's the metrics of books and other form of scientific communication. Here in scientometrics, basically it's focus on quantitative analysis of science and scientific research. Hence, when we are discussing about scientometrics, we are basically dealing with science and scientific research. Scientometrics involved different bibliometric methods to study the various aspects of scientific interaction, to various aspects of scientific literature, including its publication, citation, authors, journals and institutions. That means when we are discussing about scientometrics, scientometrics is basically applying bibliometric methods in study the various domains of scientific literature, and those domains may include the different science publication or citation or the author profile, the journal profile or the institution profile. The goal of scientometrics is to measure and evaluate the productivity, impact and dynamics of scientific research. Why do we need scientometrics? Scientometrics is needed to evaluate the impact of science. It's needed to measure the dynamics of science. It's needed to measure the productivity of science. Hence, when we say about scientometrics, scientometrics is basically measure the science productivity, is measure the impact and is measure the dynamics of science. Scientometrics provide quantitative insight into the structure, evolution and impact of scientific research. It provides how the science is evolved. When you say about scientometrics, it's a measuring of science, how science is evolved, what is the structure of science and what's the impact of scientific research on the society. These are basically the areas which we cover when we using scientometrics. Scientometrics is very much required for research productivity, is very much required to quantitatively to analyze the research productivity quantitatively, is very much required for evaluating and influencing the scientific work. What the scientific work is influencing our society, what's the influence of that work on other domain of science, this is a goal of scientometrics. That means when we are dealing with scientometrics, we are trying to find out what's the influence of research A on research B and vice versa, and it support evidence based decision making in academia, funding agency and government institution. As I discussed in bibliometrics, bibliometrics is very much essential for funders, is very much essential for the policy maker, for the planner. Similarly, scientometrics is very much required for evidence based decision making by the government, by the funding agency, by the research organizations. I am going to cover Lokta's inverse law of scientific productivity. When we are discussing about scientific laws, there are three prominent laws of scientometrics. The first is Lokta inverse square law of productivity. Second is Bradford's law of scattering of scientific paper, and the third one is Gibbs' law of word occurrence. Let us discuss Lokta's inverse square law of productivity. Lokta inverse square law of productivity is named after Alfred J. Lokta, and this is perhaps the first scientometrics or infometrics law. Lokta proposed inverse square law in 1926, which correlates contributor of scientific paper with their contribution. Hence, the basic concept of Lokta law, which is produced by Lokta in 1926, is the number of contributions made by contributor. That means the number of contribution made by an author. Lokta observed that the number of authors producing a certain number of publications follows a mathematical pattern. While proposing this law, Lokta come to know that the number of contribution made by a particular author, there is some mathematical pattern, and what he did for obtaining the data, Lokta used, he count the number of personal names in the 1907 to 1916 decennial index of chemical abstract. What Lokta did? Lokta took the decennial, that means 10-year index of chemical abstract of 1907 to 1916. He took the alphabet A and B of that particular index, and he counted the number of publication. He listed the number of publication against the alphabet A and B, 1, 2, 3, 4, like that. He treated letter A and letter B both separately and in aggregate. And while formulating this law, Lokta omitted the name of firms. That means he took chemical abstract of 10 year of 1907 to 1916, took the alphabet A and B and counted down the listed publication under the alphabet A and B. This was one source. Another source, he took the index in Felix Aureus of physics, and the basic reason for taking this, what Lokta explained, is that it covers the entire range of history of physics through 1900, and it's a quality source which only took account not only the volume of production but also quality, because it listed only the outstanding contribution in physics. That means while the first source, the chemical abstract, he took just 10-year index and took the alphabet A and B, but in his second source, that is Orbis, Lokta took the complete source starting from the 1900, and the reason behind taking this, because it publishes, it was an authentic source for history of physics and listed only the quality contribution. And while making this count, while counting, Lokta only credited the senior author in joint publication. If a publication having two or more than two authors, Lokta only took the senior author while proposing his law, while counting his number of publication against the author. Now, on logarithmic scale, he plotted the number of authors against their contribution. Because he has taken the author and the contribution, he already counted the author and contribution using chemical abstract and Abacus physics, and now he plotted the number of authors against their contribution. He found that in each case the points are rather closely scattered about an essentially a straight line having a slope of 2 to 1. He draw on logarithmic scale, he draw a straight line, he draw a straight line like that in logarithmic scale, and he found that the point is very close to this straight line which having the slope of 2 to 1. The approach of this ratio is particularly close in case of data taken from Auerbach table. The Auerbach table is quite close to the straight line as compared to chemical abstract data. Now, the general formula, Lokta found that there is a relationship exists between the frequency y of a person making x contribution. There is a relationship between the person and the contribution, and that relationship is x to the power n y is equal to constant. Let us see, this constant is c. That means when Lokta found out, analyzed the result found from the chemical abstract and Abacus physics, he came to know that there is relationship exists between frequency y of person making x contribution, and the formula for that relationship is x to the power n y is equal to constant. On the basis of this data, Lokta derived what a law, and this is termed as the inverse square law of scientific productivity. Inverse square law correlates contributor of scientific paper with their contribution. It says what's the relationship between the number of papers produced by a contributor, and that relationship is governed by x to the power n y is equal to constant. For the special case n is equal to 2, that is inverse square law of scientific productivity, the value, we can find the value of constant as you see. We have already seen that here x to the power n y is equal to c, x to the power n y is equal to c. If you are taking this one as y1, then y1 is equal to c by 1 square, Similarly, y2 is equal to c by 2a square, y3 is equal to c by 3a square, and so on. Now, if you are adding all this, that means is a sigma 1 to infinity y is equal to, you are taking c outside, it is 1 by 1 square plus 1 by 2a square plus 1 by 3a square plus dash dash dash, it's like that. Now, this one is equal to c, and this is sigma 1 by 1 square plus 1 by 2a square plus 1 by 3a square is sigma 1 to infinity 1 by x square. That is equal to c pi square by 6, and pi square c pi square by 6. Hence, for c it would be, for c it would be 6 by pi square sigma 1 to infinity y. Since here the y is frequency and the summation of this frequency gives unity, hence then we get c is equal to 6 by pi square. We know the value of pi is equal to 3 point, value of pi is equal to 3.14. If we put the value of pi here, then we get the value of c as 0.60 approximately. So, that means we are getting the constant, the value of constant here, that is 0.60. So, that is approximately 60%, is a 60%. That means what Lokta propose here, that the proportion of all contributors who contribute a single item should be just over 60%. That what Lokta wants to say. Lokta want to say that if we have the group of authors, then in that group 60% of the author will contribute single contribution. 60% of author will have only one article in their account. That Lokta proposed here. In the case he examined for the chemical abstract and the Abhikya physics, the actual proportion of this class was 59.2% in Auerbach data and 57.7% in chemical, in 57.7% in chemical abstract data under initial letter A, and 57.99% in initial letter B, and 57.9% under A and B jointly. That means what we are observing here, that is approximately 60% what we have found here the value of constant. That means 60%, approximately 60% author will have single contribution. Now, he found that if you take the total number of authors who have published only one article, then the number of authors who have published k article would approximately be 1 by k square times as the number of times the number of authors who have published only one article. What Lokta observed? Lokta observed that if we take the total number of authors who have published only one article, then the number of authors who have published k article would be 1 by k square times of number of authors who have published one article. For example, let us see, if an author published two articles. Then the number of authors published two articles would be 1 by 2 square times. 1 by 2 square times, that means 1 by 4 times. The number of authors published two articles would be 1 by 4 times of the number of authors published one article. This is basically what Lokta proposed. In simpler term, we can say that the number of authors who have published two articles is approximately 1/4 of the number of authors published one article. The number of authors published three articles would be 1/9, 1 by 3 square, that is 1/9 of the authors who have published one article. The number of authors published 4 articles would be 1 by 16 and so on. Hence, this number of authors making n contribution would be 1 by n square times the number of authors who have published one article. In very clear that the number of authors published n article would be 1 by n square times the number of authors published one article. For example, as I told in my previous slide, the number of authors published two articles would be 1 by 4th the number of authors published one article, 3 articles would be 1 by 9th and so on. The proportion of all contributors who make single article is about 60%, and this law is known as Lokta inverse law of scientific productivity. That means when we talk about Lokta's inverse law of scientific productivity, we see that most of the authors published one article in their lifetime and very less number of authors contribute most number of articles. That means a very few authors are prominent in that particular field of study who are contributing for the development of that field. This is Lokta inverse law of scientific productivity. This is the graph which Lokta originally published when he published his article in Journal of Washington Academy of Science on June 1926. You see here, this is the fully drawn line and this is the dash line. This fully drawn line is basically indicates the point given by inverse square law. Now, as I mentioned that Lokta evaluated two sources, one is Arabic and the other was chemical abstract for letter A and B. In Arabic, this crossed, you see all this cross, basically these cross are for the Arabic physics, and this circle, this particular, you see this particular circle are for chemical abstract. What you are finding it here, that means in case of Arabic, the cross is very much near to this fully drawn line, while this one in case of chemical abstract, these circles are very near to the dashed line. That means when we are drawing a graph on logarithmic table using the data derived by Lokta, then we come to know they are quite close to the exponential line having slope of 2 by 1. This is basically Lokta's inverse law of scientific productivity, which is very much essential for growth and development of science, and which predict the how science is moving, who is the most prolific author, who are the author who are contributing in science. Now, if you see the various applications of Lokta law can be used for research evaluation. Lokta law can be used for evaluating research productivity and identifying the highly productive authors, because we have already seen that some of the authors are contributing the maximum number of articles in a particular domain of science. With the help of Lokta law, we come to know who the author are and how they are contributing in science productivity. Lokta law can be used for authorship analysis. We can analyze, we can understand the authorship pattern in that particular branch of science using Lokta law in scientific publication, how that particular scientific publication are happening, who are the most eminent author, who are the scientists, who are the researcher, who contributing for the development of the domain can be found out using Lokta law. Lokta law can be used for the resource allocation. Its help in taking the logical decision for the allocating of the resources, because based on the Lokta law we can find out the author productivity, and by that way it possible to take the decision on allocating of resources. Lokta law gives the research trends and the research pattern. With the help of Lokta law, we can find out the most prolific author, the most contributing author, and by that way we can find out in which particular domain that particular author is working with. By that way we can find the research trend and pattern in that particular domain. Lokta law can be used for the career development, is used for the mentoring, because Lokta law find out the productivity of the author, and based on that we can find who are the most eminent author to whom we need to pay attention. It provides the insight of the career development and the mentorship program. Hence, Lokta law can be used for the career development and the mentorship. Lokta law can also be used for the publication strategy. Lokta law can guide publication strategy for the researcher. They understand the distribution of the author productivity and can set the realistic goal. You see, every discipline is unique. It's not necessary that discipline A is contributing more, so that discipline B in science. They having their unique characteristics, they having their unique feature. With the help of Lokta law, a budding author can find out, can derive his or her strategy and work on that. He or she can fix a realistic goal based on the development of that particular domain, which can be achieved by him or her in next 15 or 20 years of time. Lokta law is used for the bibliometric studies, like we have already covered that bibliometric study like authorship pattern. With the help of Lokta law we can come to know about the authorship pattern, we can come to know about the production, which are most productive field we can come to know about the productivity distribution, we come to know about the collaborative network. All these are possible with the help of Lokta law, and Lokta law can be used in this category. Lokta law is very much essential for the management of library and information centers. Library and information management, Lokta law helps in management of library and information. This can be applied to analyze the productivity of authors in academic library and information management, and this can be useful for the librarians and information specialists in research allocation and the collection management. You see, we know that with the help of Lokta law, we can easily find out the author profile. We can easily find out how the author are performing in particular domain of research, in particular domain of science. Hence, the library information science professional use Lokta law in their collection development, use Lokta law in the resource allocation, use Lokta law in guiding the institution to adopt different development field where the further study can be done. Lokta law can also be used for making a good information storage and retrieval system, because a good information and storage and retrieval system is very much required to retrieve the stored information precisely, and is very much required for getting the required information in the right time, in the right way. And the Lokta law can be used for the search engine by understanding the distribution of authorship and improving the ranking of search result. You see, a good storage and information system is that which give you the maximum precise result with minimum time, and for that Lokta law can be used for improving the search result. Lokta law can be used for ranking the search result. By that way, it would helpful in making or in designing a good information storage and retrieval system. There are some limitations of Lokta law also, because we have already seen that Lokta consulted two sources, and these two sources, having one was chemical abstract, other was is a qualitative based physics literature. In first, there was 10-year index, covered only letter A and B. In the second, he covered the history of physics without any restriction on the letter. Hence, for Lokta law, single source in a limited time frame may not produce favorable result. It's important, because I have already told you in the beginning of my lecture that science is ever growing, science is dynamic, science is expanding. Hence, if we are taking any source for a limited period of time, for 1 year, 2 year, then the result which we obtain won't favor Lokta law. If you are taking a single publication for a given journal, then the Lokta law, it might be possible that Lokta law won't be true or correct, it won't follow the Lokta law. Data compiled from a comprehensive source in order to capture true representation of author publication using either quality or quantity as a selection criteria. Lokta law is valid when we are considering various comprehensive data for a longer period of time, then the Lokta law can be true, or it can be it can give true result. Another limitation of Lokta law is assumption of stability. Lokta law assume a stable system over time. You see, when Lokta proposed his law in 1926, basically he took chemical abstract 10-year data, the another physics source having the data from the 1900 onwards, but science is dynamic. Hence, he assumed the stability of science basically. Lotka assumed a stable system over time, but that system is not stable. If we are taking the data of 1907 to 1916 of chemical abstract today, it not necessary that whatever produced 100 year back would be true this time also. That means we can't assume a stability in case of science because it's developing area. Hence, without taking a stability, without assuming a stability, we can go for the Lotka law. But Lotka law, when he proposed, he assumed the stability because he took the data of limited period. Lotka law is basically a linear model. It's based on the power law relationship, assuming a linear model for the distribution of scientific productivity. This may oversimplify the complex nature of scientific productivity. You see, Lotka only counted the number of publication against the contributor, how many article is published by a particular contributor. But science, the nature of science is something complex. It's not only limited to the publication, number of publication by a particular author A or B. Hence, whatever the model proposed by Lotka is something which is very much linear in nature, and this was one of the limitation. He made it so oversimplified that he didn't consider the complex nature of science while proposing this model. So this was one of the limitation of Lotka law. There is another limitation of Lotka law, and that is the dependence on data quality. The law highly depends on the accuracy and the quality of data so obtained. Incomplete or inaccurate data gives the false result of Lotka law. Hence, is quite dependent on data quality, and basically it's static analysis because the law is more suited for static analysis instead of the dynamic analysis because it doesn't capture all the changing mode of science communication. Thanks for your patience hearing. Thank you.